And we move to the second speaker. Anna, please. This one.
Okay, great. Thank you all for coming and listening to my talk and for great no bugs so far. I'm going to be presenting on how the advanced photon source is creating automated data processing pipelines to leverage high performance computing. And this is to address our increasing data needs and for us to be able to enable scientific discovery. Oh, are we? So why does this matter? We started tracking experiments in our data management system about 10 years ago. And you can see here from these charts that the amount of data that our facility is responsible has continued to grow. And over the years, you can see it just going up. And then this plateau over here is when we started our APSU shutdown. And then recently, you can see this little dip where we started to archive our data. But in addition to having these large volumes, we also are expecting that over the next decade, after our upgrade project, we're going to need tens of petaflops of on-demand computing power as well to address this. So we have a APS data management system, which is responsible for a variety of things. This can be moving data from place to place or managing the storage, tracking what's going on in the experiment. But what I want to draw your attention to is the workflow tools that we have for processing data. So this could be automatically as the data is collected, or it could be some user-initiated tasks. And then it also allows us to execute these jobs locally or remotely. And one of the neat integrations that we've been providing recently is to integrate with our Blue Sky control system. So what this means for our users is as they're running their Blue Sky plan, they can get their processed data right away and they don't need to follow any extra steps. We've also integrated with Globus Compute. You got to hear about Globus this morning and all of the different capabilities that it provides. But what we use Globus Compute here in this case for is to allow us to execute jobs on remote resources. So the advanced photon source, it's a world-class light source, very powerful and awesome, but we are in a really unique situation where we share our campus with the Argonne Leadership Computing Facility, and this houses some of the world's most powerful supercomputers. So we've established a very strong partnership with the ALCF, which has allowed us to do some very unique things. One of this is that we have an on-demand queue, which you may have heard mentioned briefly. And what this means is that while you are running your experiment, you get that quicker access to the data. So you get put into a special queue, which can steal nodes from other jobs. And this gives more of that near real-time processing that we want to achieve. And then we've also created some service accounts for each of our beamlines and have a specific computing allocation just for the APS. Because HPC is not a skill set that we expect most of our users to come in with, and really they're coming to perform an experiment. They're not there to do simulations or do HPC tasks. They really just want to see the end result. Another really strong partnership that we have is with Globus, and this has allowed us to use some of their tools to help with this remote execution. So Globus Compute provides a function as a service platform. So this means we can deploy endpoints on the remote resources and then submit tasks to them. And this allows us to automate getting access to those machines in a way that is secure. So here I'm going to show how we've integrated our data processing with our controls. So we use Blue Sky, and it already knows a lot of the information that we need. It knows where it's going to be writing files. It knows different things about the experiment conditions, and it's already tracking different metadata fields. So this information can be passed along down to the downstream processing without the user having to be moving that information between the systems. So basically how this works is that in your Blue Sky plan, there is a set of APS tools, and this gives a connection to our data management API, which will then go ahead and launch your workflows. So I'm just going to walk you through what this looks like in process. What is the data lifecycle at the APS? So when the users come and they're sitting for the experiment, they're going to be filling out some information about what they're doing, their safety form and their proposal. And then we're going to use that to set the experiment up for them in our database and allocate some folders for them in our central storage. And then we start to monitor for files, and Blue Sky goes ahead and it starts the experiment, and it does what it needs to do and acquires the data. And then from there, we transfer the files locally to our central storage, and then it will pass along the workflow arguments and launch the processing. These jobs could be running on a computer at the beamline, or it could be launched over to the ALCF. And then one thing that we have here at the end that we're hoping to get some more of are some very nice data portals. So this means that the user can have a nice way to view the results and see what's actually meaningful to them right while they're sitting at the experiment. Then after some time, the experiment will end and the data will be moved to our archive on tape. So the goal here really is to provide a way that we can standardize our processing and have it be reusable across the many different X-ray techniques that we have. So we have a lot of different beamlines around the ring that are shared by the same group, or they're doing the same sort of processing technique. So we want to be able to standardize these packages and wrap them up so that we can easily deploy these across the ring. So you can see here a number of different beamlines and techniques where this has already been deployed, and then also a few that we still have to come. I want to bring your attention here to one specific use case which really highlights why this is important. So in this use case, this was Lowy diffraction using a coded aperture. And my colleague Michael Prince, he put a lot of effort into optimizing this code, parallelizing it, getting it to run on GPUs. And then running over at the Polaris supercomputer, this used 50 nodes during the beam time, and this is about 4 petaflops. Basically, what this means is that this sort of processing and for this technique would not have been possible without these sorts of resources. So this is not some job that you could just run locally and get your result. And really what this means is that these tools that we're building and the reason why we're doing this sort of model is because it really does enable us to do new science. Another great example is our cross-facility collaborations. So this one is one that you saw where we were able to use the Tygadus package, and this can be run at different facilities for experiments. So at the LCLS is where the data was actually collected, but then it was shipped over to Argonne automatically, and the processing occurred, and then the results came back. So this is one way where we can have these sort of partnerships where your experiment and your computing don't necessarily need to be taking place even in the same size of the country. So here is what some of these data portals look like. So these are built with the Globus Django portal framework. So this is another reusable framework that Globus provides for accessing some of its data on its endpoint. And this is great because it is a searchable way to see your data and to visualize it, but it's also got the secure access using Globus groups. This is something that we do customize for each beamline so that they get a view of what they actually care about. So it's a close collaboration with them. We're also aiming to have a multi-tiered approach here. So we recognize that not every single computing task that the beamlines care about needs to run on a supercomputer. There's some things where we have some edge computing devices. We have a few high-performance workstations that are sitting directly at the beamline. And then we also have the Argonne Laboratory Computing Resource, which is a different computing center. And we have a local cluster. So this means that if you don't want to send your jobs over to Polaris, you don't have to. But what's great is that over the next time as the Argonne Leadership Computing Facility is bringing Aurora online, we are planning to take over the Polaris supercomputer, and this will give us access to even more computing for our beamlines. Some future work is that we want to expand the use of our data portals, and we also want to integrate some of our existing data management features into this web UI so that users can manage their experiment data all in one place. We also have plenty of more workflows that we want to deploy, including the use of multimodal techniques using combined X-ray techniques. And then we have a streaming framework for processing, which is the PVA Pi streaming framework that uses epics. And this is something that we're looking to develop more use cases for. So I'd like to acknowledge all of my collaborators over at the ALCF and in our Data Science and Learning division, and also everyone at Globus who helped to make these possible. Our many Beamline staff who sat together with us and told us about what they're doing to make this something we could build for them. And then also our technical staff. So what questions do you have?
Too many petaflops.
Right, okay, so one of our many 200 workflow engines is that we do have our own workflow engine. Yeah, so this is something that was already a part of our data management system. So when we do want to use the Globus flows, so that does provide its own workflows, and we basically just chain them together.
I have one myself.
Yes.
Just a curiosity. What's the latency in between finishing a data acquisition, you send around all the data package, and then you get back the results? How long it takes?
Yes.
Seconds, minutes?
Usually this will depend largely on what kind of time is in the queue. So that would be like the main waiting factor. There is a little bit of time just transferring the data, of course, and then there is some overhead from Globus. So this could be a number of seconds for each task, but then what would really make it be up to minutes would only be if the queue is full. So really, this is a case where if you had a very large computing tasks where it needed that large processing, then you wouldn't really you wouldn't care that it was a couple extra seconds, but if you really want that kind of real-time feedback, this might be where you would want to process on an edge device.
Thanks. Any further questions? Oh, one quick thing.
Maybe more of a comment. This differentiation between real-time, near real-time is sometimes still hitting us. As soon as we let users process on the HPC cluster, they will get used to this happening within minutes, but sometimes when the queue is full, it doesn't. And then if they've built their real-time feedback or real-time-ish feedback based on the assumption that's always there, that's where things get stressful. So I think keeping in mind that you need some edge computing is really good that you're mentioning that, because otherwise there can be frustration both on the user and support side.
Yeah, absolutely. Thanks for sharing that.
So let's thank Anna again.
Thank you.